more.
Okay.
It's not like I'm looking in.
Double check. Okay, so welcome to this crash course. Has everyone filled out the rego form?
Yes.
Okay, cool. So when's your first, what's the word for it? Workshop?
Tomorrow.
Okay, tomorrow. Have you guys looked at the middle yet? Okay, well, you're in for a surprise because they changed the courses here. There's a quiz in week 3 during your third workshop, right? And it's basically at whenever your workshop is, say it's at 4 or say it's at 6, you get 2 hours to sit it, upload, and that's it.
Is it
Right?
like
So it's basically an intern.
yeah, it's like it's a collect quiz.
Yeah,
They call it as an assignment though.
yeah, it's not an assignment basically. It is. But it requires you to scan and upload. So that's my goal today, to try to prepare you guys so you feel ready for that. Okay. So with that in mind, hopefully that scares you a little bit, because it will make you focus a bit during this. Okay, I'll just give you a bit about my background, right? So I know a few of these guys through Substock. I graduated like 2 years ago. I was part of the society and all that. And I spent a year last year working full time as a structural engineer, like a graduate, and I decided to come back and I'm doing a PhD. I really liked teaching when I was an undergrad and continuing teaching, but I'm not teaching as a demonstrator for steel, so I'm teaching for like geotech and solid and desert. That's a bit about me. In terms of this course, right? So essentially, if you've gotten this far, you've probably done Edge 1300, right? And you've probably done solid mechanics, right? Those are probably the 2 most important courses for doing this one. You might have done 2303, which is structural analysis, right?
Yeah.
That helps, but it's not necessary. So if you haven't done it, don't worry. It's mainly solid mechanics and hinge mechanics, specifically the statics part that this really builds on. So this is your first taste, most of you, I know Andy, you've done concrete. This is your first taste of a design course. And when I say design course, I mean a structural design course, right? So there's 2 core structural design courses. It's concrete in term 2, and this one in term 1. Okay. There's going to be other design courses that you're going to experience this year, assuming you're 3rd or 4th year, like water-related discipline ones or transport ones. And to be honest, it's a really exciting time. Like, I really enjoyed the year, so make the most out of it. What you will find is essentially you're like a blank canvas, right? Like, you kind of want to be a civil engineer or something like that. You might be enviro leaning, or you might be whatever. You might be architecturally leaning or whatever. But you're essentially a blank canvas. So you walk into this year and you're like, what kind of major do I want to specialize in, right? So there's several. The one that really drew me in was structural engineering. I like the elegance of it. I like how everything ties together nicely. You kind of work from first principles physics in order to justify everything. Everything feels very fair. It feels like all the effort you put in like doing these calculations, refining them, getting really quick at them, it pays off in your marks. It'll be reflected if you study hard for this course. It will pay off. That's what I really liked about it. There's some other disciplines, let's say construction, which might be more like vibes based. Like you might hand in an assignment and you have no idea what you're going to get. Things like that. It could be more strict, etc. That's why I like structural. So I did this course a little bit late when I was doing my undergrad. I was doing it in my 4th year because I did solid mechanics late because I did a double degree with commerce or whatever first year. Anyway, it's a whole story. But I did it late, and I didn't realize that I liked structural engineering so much until I did this course. So today my goal is to convince you that this course can be a lot of fun, even if you don't want to be a structural engineer in the end. Hopefully you can see the benefit. You can get some benefit out of it, right? Okay. So I'm gonna run through the weeks now. Does anyone have any questions just generally? It can be non-technical related, it can just be career stuff. Okay, so feel free to ask me afterwards if you want as well. Okay, so all the weeks laid out. It's essentially what I want to cover today is week 1 and 2, right? Just kind of compress it. Normally you get 3 weeks to kind of digest tension and compression, designed for steel. But you only get 2 weeks because essentially your 3rd week is quiz, right? And later in the course, week 8, that's essentially, you don't get a workshop either because it's another quiz, right? So everything's just like going to be accelerated, right? That's the idea. Same content, I'm pretty sure. Assuming, like to my knowledge, it's the same content. It's just, you're going to have to hit these beats rather than there being like long-term assignments you kind of chip away at. And then you'll reach the finals and you kind of have to combine everything that you've learned, okay? Any questions? Yeah, so that's the way it works. So let's get more specific, right? So I mentioned tension and compression design. That will be a part of what we're going to do today, and it's going to be what feeds into your first quiz, right? But I would like to just give you a bit of an introduction into structural engineering, and then I would also like to introduce to you guys the concept of load combinations. Load combinations is a structural specific concept. Yeah, and you'll need it for this course, you'll also need it for the following course, concrete. Okay. And then we'll do flexural design. We might not get to cover it today. What I'm hoping to do is like produce a bunch of videos which kind of cover all these. So subscribe on the channel. But yeah, we'll cover that later. There'll be flexural design, shear design. We'll talk about steel connections and this concept of beam columns. Okay, so that's the scope of the course. Okay, so like, what do we mean is a structural engineer? Is a structural engineer just another middleman to basically shove blame onto? Partially yes, but here's the way it works. Okay, so you have a client. Let's say it's a government client, like Transport for New South Wales. They would be responsible for something like a bridge, right? And developing the infrastructure for it. So that's the end client, okay? They approach an architect, an architectural company, who basically does, like, makes it pretty. Like, okay, this is what our bridge is going to look like. We want it to be beautiful and win a bunch of awards, and so our company gets lots of good reputation, etc. Right? That's the interest of the architect, right? But as they go on throughout the project, they'll realize, oh my god, there's so many engineering constraints, and I hate engineers, and etc. So that's the way it works. They produce something called architectural drawings, right, which describes essentially how the whole thing's going to look in the end, and it will encompass a bit of how it's going to be built, a little bit. Okay. More so, the engineering drawings are going to dictate how it's going to be built. So that's what a design structural engineer does, right? They develop structural drawings. Okay. If it's a small company, it will just be a structural engineer doing, like, you know, have you guys heard of like AutoCAD, Revit, those kind of things? Structural engineer will do that as well, but that's called drafting. That process is called drafting. In a slightly big company, you might get dedicated drafters who specialize in that software, right? So that the engineers can just purely focus on calculations and etc. Okay. So that's kind of how that works. Drafting, by the way, is like a TAFE qualification. So if a company does hire drafters, they're usually like from a TAFE background and stuff like that. Okay. Site engineers. So some of you guys might not end up being design engineers, right? You might prefer being on site and, you know, like being out in the sun and communicating with like all kinds of parties, and especially like, you know, if you're extroverted, like talking to people, this is a pretty good route. Get paid a lot as well. They're essentially the interface between structural engineers as well as what about other design engineers like water engineers and builders. Okay, so the site engineers are going to be the ones who are basically they have a fundamental understanding of how the engineering works, right? And they're the brains of the operation, whereas the tradies and the builders and whatever they're doing the heavy lifting, right? The site engineers also schedule everything, make sure the materials are ready, so that it's a smooth construction operation. Make sense? So even if you don't specifically want to be a design engineer in the end, it's good to know it from the design perspective. Like, it's good to know what the structural engineer is essentially designing for, or where these numbers even come from, right? And lastly, you got the Steelfixers, right, who basically are assembling like Legos. They're the ones who go on site and do the heavy lifting, and they're putting the connections together, putting steel members together, fabricating it according to this instruction manual, which is essentially your engineering drawing, and they're putting the pieces together. Okay? Yeah? Well, okay, so that's why this is important. Okay, so next, let's talk about, one second. Let's talk about structural capacity equation. So for those of you guys who sat in the previous workshop, during Farhan's talk, he was talking a little bit about this, right? So the structural capacity equation. This is a pretty fundamental structural concept, and essentially, you're comparing two numbers. This is what it ultimately comes down to. You're comparing the strength of the structure, how strong it is, right, versus the loads that you're expecting it to take on, okay? So on the left-hand side, these are your loads, right? This might be cars, humans, bikes, animals, whatever. On the right, this is your capacity, okay? So that's how strong something is. So I'll give you an example. The one that I typically talk about, everyone's watched some of these videos before. Imagine scaffolding, okay? Imagine you have scaffolding, and imagine it can support exactly 100 kilograms of load, okay? That's what it's designed to do. Oh, actually, wait, sorry, scratch that. Let's do 300, okay? I know this is in kilograms and not in like newtons or kilonewtons, but just bear with me. I'll just say kilograms, so it's easier to visualize. And we have 3 tradies, right? And they're like big, heavy tradies, and they're all like 100 kilos. And eating their meat pies and Monster energy drinks and stuff like that. Basically, yeah, you might be able to see the problem with this scenario, right? Your structure can only take on 300 kilos of, like, it only has 300 kilos of strength or capacity, we call it, right? And these 3 guys are standing on it, and they weigh 100 kilos each, right? So there's a good chance it'll break, you know, but what we can do as engineers is we can put in this factor of safety, essentially, system. And there's different systems. There's the geotech system, which you'll learn when you're doing geotech. They just do factor of safety as a number like 2 or 3. But then there's also the structural system, okay? This is broken into 2 sides, right? So we have this, again, this is like a inequality, right? Left side, right side. On the left, we want to exaggerate our loads, okay? Let's just say, even though these tradies are 100 kilos or whatever, on a good day, they might be 120 kilos, you know, eating a lot of McDonald's and whatever. So you have to account for this, right? They could be heavier than expected, or they could be more tradies than expected, or whatever. So we have to basically exaggerate how heavy it is in order to make our structure safer, right? When we're designing for it. The other thing is, on the right-hand side, we have something called the capacity reduction factor, right? Which is about pretending our structure isn't as strong as it actually is, okay? So instead of 300 kilos, we might call this only being like 250 kilos. Actually, what I might do is I might say, we'll only pretend it has 90% of 300 kilograms of its strength. Does that make sense? So that's what that is. That 0.9 is your capacity reduction factor, essentially. Right, so instead of saying like 270, right, I've just said 0.9 times 300. Okay. So, you know, given that this 3 tradies 120 kilos, and you know, we're actually going to pretend it's bigger than it is, what we'll say is we're only allowing 2 of these tradies to be on this platform at once. You know, that's what you'll end up being in the end.
Is there a reason you're factoring both sides of the equation? Like, why can't you factor one side more?
It's a good question. It's because different, fundamentally, loads and different materials will have different levels of something called reliability, right? So if that's made out of steel, let's just talk about the capacity of the material, right? If that's made out of steel, essentially you can deduce that it's going to be more consistent of a material than if it was made out of wood, okay? So wood has a lot of defects. Wood has knots, natural defects, you know, like the little, I'll draw it. So there's the grains of wood, and then you might have like a knot in the wood. Have you seen that before? In a plank of wood?
Yeah.
That's a structural defect. So it actually could cause your bit of wood to be weaker than it actually is, right? So wood generally speaking, would have something more of a factor of safety of 0.65, right? Whereas steel has 0.9. Okay, so that's one. So materials can vary, and the other thing is loads can vary as well. Okay, I'll go into this when I talk about live and dead loads, but basically, wind loading can be more inconsistent, for example, than actually no, that's a bad example because in Australia, yeah. I'll go back to the left-hand side. Okay, I'll talk about that in the next one. Just because I have a bunch of stuff on the next page ready for it. Are we all following? Yeah. So that's why we have this two-part kind of system. It's because the loads will vary in one way, and then the materials will vary in another way. Okay. Okay. So this is it basically. There's this. Oh, sorry. I was going to talk about all this stuff. Okay, I was going to talk about this mainly. So this is the first course where you guys are going to be exposed to Australian standards. So that's basically a big booklet which says this is how you're allowed to design things, right? Like you can't make a structure which can't tolerate these loads and isn't strong enough to withstand, these loads or whatever. It's a book that outlines all the rules. And what we do in uni is, in this course and concrete and all the other design courses, we teach you those rules. So straight from the book, okay? And one of those books is AS 1170.0, and that's the load combinations book, okay, specifically. And AS stands for Australian standards, right? It's going to be different to the Eurocode, which is for Europe. It's going to be different to ASI, which is for American codes. It's going to be different to Brazilian code, Chinese code. Yeah, you get the idea. So this is specific to Australia.
So wait, that 1170 specifically, that's for load combinations?
Yes. So load combinations, and that will be what I'm talking about next. So load combinations are going to apply to loads in general. It's not going to be specific to steels, okay? So this will carry on to your next course. This will carry on to concrete, right? So there's a few different types of loads that we will cover today. I'm going to talk about G, Q, and W. Okay? G is your dead load. Q is your live load, and W is your wind load. Okay? So dead load is basically something which is put in place and it's not going to move. Okay? For usually the span's like 50 to 100 years. Okay? So, for example, for the remaining life of the structure. So say this building, right? We have the weight of that concrete column or something, right? It isn't going to move because it's part of the structure, and if the structure was being demolished, then we wouldn't have any use for the other structural components. So that's essentially staying there. Okay? A live load might be a human or a car or something that's going to move from place to place. It could also even be this whiteboard that's on wheels because it can move around. Okay? So live loads are free to move around. And so we want to factor these differently. We want to treat them differently because live loads can vary more than dead loads. Okay? So I'll answer your question in a second. Live loads, for example, in an elevator, the elevator you used to come up here, you could randomly have like 20 people in there one day, right? Or like 30 people if you just cram a bunch of people in. So that would be considered a live load because it's just the fluctuation like is much bigger. Okay. Any questions with that? Did you have a question?
That was a stupid question.
Oh no, sorry. Okay, all good. Okay, and the third one we talked about is wind load. Wind load is actually pretty complicated, but in this course we're just going to treat it as a flat number. There is ways to calculate wind pressure based on terrain and like whether you're in like Sydney or like Brisbane or whatever. It's going to be a flat number. Okay. Wind pressure, in the context of this course, it might be on a wall. Okay, so let me draw something. You might have like a street sign or something, okay? And it's copying a lot of wind. So these are arrows, like force arrows, like going into the sign or whatever. and that's like a uniformly distributed load or whatever, right? So wind could be pushing against the sign or something, right? For example. Wind can also be acting on the roof of a building, for example. Okay, so you could have suction, right? If you have a decrease in internal pressure of this building, it wants to suck in. Oh, sorry, suck in is down. Anyway, or it could, or if you have an increase of the pressure inside a building, it could cause wind to want to. The wind pressure could cause. Sorry, the increase in pressure could cause the roof to want to come off, basically. Right. So there's different directions that. There's different directions that wind can be applied: up, down, against the surface, etc. Okay. So just keep that in mind. But it's all described by these load combinations. Okay. So those are the different types of loads that will be factored. Okay. And in a question, they'll give you the unfactored loads usually. Unfactored means we haven't applied the 20% increase in this load combination or whatever, right? They'll give you the unfactored loads, and then you have to factor them yourself. Okay. So, actually, wait, sorry. Can someone turn on the fan? I actually really want to. Oh, no. Thank you. Okay. So, this little snip on the left is from the Australian standards, the standard I was telling you about, 1170.1.0, and describes all these different cases, okay? So the first one is dead load governed, right? What it's saying is, if we have a scenario where there's only dead loads, we're going to exaggerate everything by 35% in terms of loads, okay? That's scenario one. Scenario two, if we have dead loads and live loads acting together, okay, we're going to exaggerate the dead loads by 20% and exaggerate the live loads by 50%. You guys see where that's coming from? So that's coming from 1.2 and 1.5. Got it? Okay, another one that we run into pretty often is the wind and live and dead loads. And basically that's when you have your wind is like causing, say, the roof of your building to be pushed down in the same direction as gravity. That's when they're all like acting in combination, and that's what this load combination is describing. So it's basically 1.2 G plus the wind plus this thing Q. So that's called a load combination factor, which I'll show you below. Okay. And this last case that you should think about is something called wind reversal. Okay. This one's kind of interesting because it's the only one where the dead load is under exaggerated. Can anyone think of why? And it's called, and the hint is it's called wind action reversal.
The wind is moving up.
Yeah, exactly. Right? That's perfect. Okay. So say you have the roof of a building and the wind's actually blowing up, right? Suction. It's like pushing the roof of the building upwards. The dead load is actually beneficial. The dead load is actually helping in this scenario hold the roof sheeting down. So that's why you actually under-exaggerate the dead load, because it might not fully be installed or whatever. It could be less dead loads than expected. So that is when it's wind governed, the wind's reversing the normal gravity action, and the gravity loads, like the dead load, is actually beneficial. It helps your system not fail. Make sense? Cool. Alright, cool. Okay, so, oh yeah, let me explain what a Purlin is quickly. So, okay. Basically, Purlins are, you don't have to know too much about this, but you have a roof, right? You have a steel frame roof like this, and you have something called rafters, which are basically big fat steel beams that kind of frame the building like that, right? They're attached to columns usually, like that, okay? And the secondary members which join these together, they're called purlins, okay? So that's what you're looking at here, and that's what you're looking at here, okay? So these are secondary steel members, whereas the rafters were the primary steel members. Okay, but they're just beams, basically, right? Okay, I bring that up because that's what the cross section looks like. This is a C Purlin, right? Let's focus on a simply supported Purlin, right? So it's a simply supported beam, and it's 3 meters long, right, from support to support, and it's experiencing dead load, live load, and wind load. Okay. So dead loads are 0.15 kilonewtons per meter. Live loads is 0.25 kilonewtons per meter, and wind load is 0.5 kilonewtons per meter. And we have to consider the up and downwards case. Okay, that's where that plus or minus comes from. Okay. For roofs, right? So this is from the code. I'll show you guys later where this is from. The combination factor is 0. Okay. I'll show you that after this. Okay. So what we have to do is we basically have to find your biggest number that's going to govern your design. Okay. And the way you do that is through the load combinations. You check combination 1, 2, 3, and 4. Okay. So it's like this. We can plug in our distributed loads. Keep in mind this is in kilonewtons per meter. That's the units we're working. And this is a live load. That's 0.25. Combination factor was 0, and the wind loads were 0.5, and in this case, does anyone know what to plug in for this one? For the bottom one? Bottom wind?
Negative.
Yeah, exactly. Negative 0.5. Okay? It's negative 0.5 because it's acting in the opposite direction as the beneficial dead load. Does that make sense? Okay. So, that will be past these numbers. Okay, so looking at these numbers, which load case governs? Number 3? Yeah, that's right. So basically, we want to find the biggest absolute value, right? So if, for example, that that number ended up being like 0.85 or whatever, negative, that would be the governing load combination. Okay, makes sense?
So if the negative is just direction.
Yes. Yep, exactly. It's just direction. Okay. So the notation you have to get familiar with is this little asterisk, right? The asterisk is factored, right? It means that, okay, we've considered all the load combinations. Now this is the governing one. This is fact. Okay, that's what that asterisk stands for. So, okay, that's basically all load combos is. Oh, you better take that. If you need these notes as well, we can link it as well at the end of the workshop. Okay, tension and compression numbers. Okay, so like what makes this course different from early courses is we focus a lot more on like real life examples, and in fact I think Brian like kind of encourages it based on how the questions that he gives, like assignment wise and finals wise. There's usually like a very practical component to it, so you kind of want to absorb as much as you can in terms of the practical application, right? So tension and compression members, like tension and compression are just types of loading, right? So for example, here I've got like a bit of wood, right? So this is like a solid material. If I'm pulling on it, that's tension, right? Like I'm pulling in both directions, it's straightening out. Okay? Compression, right? I'm pushing it together like that. And what you see is it starts to buckle. I'm going to talk about that very briefly. But you're going to see this in compression members which are very slender, which means very skinny and long. Okay. So, why does the external forces kind of govern what something looks like or what something's designed for? You know, like for example, a simply supported beam, or like the Purlin that you saw earlier, you're not really expecting a compression load on these types of beams because it'd be so random, you know. Or Like it literally have to be like a car crashes into the beam sideways or something to induce compression. It's not what it's designed for, right? So these members are designed for specific types of actions, is what we call them. Actions are like loads, right? So compression, tension, shear, bending, all that. Okay. So these members are optimized to withstand these kind of loads. So we end up getting roughly, like generally speaking, three types of members, you know, out of this. The first one are hangers. Okay. So this could be a sign that's hanging. It could be that projector or that fan, right? The metal kind of rod that's holding it up is a tension hanger. Okay. Because you know the gravity, the self weight of that projector or the self weight of that fan is basically elongating that metal rod, right? So it's essentially, a tension hanger. Okay, so that's the first one. The second one is a truss member. Actually, I'll talk about that last because that'll probably require the most explanation. Another one is columns, right? So essentially, if you think about a stack of children, don't worry about it. I'll explain it. It'll make sense. If you think about three toddlers or whatever, and they're giving each other like shoulder rides, okay? Which toddler is experiencing the most weight? The one on the bottom. So what happens when loads want to transfer from one thing to another, right? So the top toddler down to the ground, is that they basically get stacked up, heavier and heavier. So that top toddler is only experiencing its own weight, and then the toddler underneath is experiencing the weight of itself and the toddler above, and then you know so on and so forth. Like the bottom toddler is experiencing all the weight. So this is actually why in buildings, if you look at the skeleton, the structural skeleton of a building, you get these columns that have increasing sizes. Okay, because from floor to floor, essentially that top column is only copying the weight of the roof and itself. The next column is copying all the red things that I've highlighted and the weight of the floor, and itself, and so on and so forth, right? So you get this increasing column size. So I'm talking, like in this context, I was just talking about a concrete column, because you can control the size of concrete columns pretty well. You know, you can cast concrete in whatever shape you want, basically, right? But a similar concept would apply for steel as well, right? Okay, so that's columns, right? They're compression members, right? So they're going to experience compression. Last one is truss members, right? Which are a little bit more nuanced. It's a little bit harder to kind of grasp when a truss member is in tension or compression, but you guys aren't like, you know, complete strangers to trusses. You've probably seen them before in Edge 1300 or whatever. But I'm going to try to run you through the logic of how you consider, you know, tension and compression in these members without doing any calcs at all. Okay. So firstly, let's just say we have this triangular like apparatus essentially for a truss. You know, it's just got three truss members and it's simply supported, and we have a force coming down from the top. Okay. So what happens is what we can do is we can draw its deformed shape. Essentially, it wants to sag down the bottom, right? And it's getting squashed from that load at the top. So that bottom member ends up being in tension. I'm exaggerating the deformation like significantly, by the way. And these two members are being compressed. Okay. So this was actually an assignment question last year, right? Like this pretty much exact system. And what they told you to do is like this is member 1, 2, 3. It's like design member 3 as a tension member, design member 2 as a compression member. Make sense? Yeah. And they tell you all the details, but like that's essentially the idea. So truss members can be in tension or compression, right? And when I'm talking about tension and compression, I'm talking about pure tension and pure compression. All the load in a truss is transferred axially, right? So none of it through bending. Okay. Yeah. Okay. Any questions? Okay. Time. Okay. I'll finish this page and we'll take a break, right? So capacity of tension members, right? Okay, so I'm going to draw from your knowledge of things that we've already talked about. Okay, so we've already talked about load combination. So the left-hand side is solid. That's what I was talking about with like the wind and the live loads and dead loads, and we factored all those actions already, right? Okay. So the right-hand side, now we're going to talk about this, and this is where this course is uniquely Steel's, right? This is where it's different when you're talking about concrete. It's different about when you're talking. I'm tripping over my words. It's different when you're talking about timber structures. Okay, so this right-hand side will vary, right, from material to material, from standards across the world, from standards across the world. Okay. So the first thing, as we discussed earlier, we have this reduction factor. Okay, so that's one thing you can just pull from the table. For the case of tension, in a steel member, this is 0.9, right? So we're just going to pretend it's 10% weaker than it actually is. That's just a flat rule. Okay. Next is how do we get this thing? How do we get NT? Right. That's the capacity of it. Okay. How do I get this? That's the question. Okay. So from N to 2400, which is solid mechanics, right? Do you guys remember the equation for stress? Like just normal stress. Yep. Nice. Okay. So we know stress is your force over area, right? If we want to rearrange this for force, right, it's stress multiplied by area. Yep. So let's just give these some units, right? Let's say this is in newtons, and this is in millimeters squared. This would be an MPa. Right. So now we're going to deal with this in MPa, this in millimeters squared, and we have something in newtons, right? Okay. So here's where the notation will change depending on standards and whatever, but this is the basic principle. NT is going to be a force, okay? This is basically the max force it can take. That's what we're trying to say. This is the capacity. And that will be in newtons, let's just say. Okay? This stress is going to be Fy. Okay? So I'll show you that in a second. It's on the next page. Fy is basically its yield strength. Okay? So how much stress it can take before it yields and turns into like this plastic cheese kind of shape, right? Like it's just like yielding basically, right? And area, right, is going to be AT, area and tension. Okay, so just to reiterate, we're talking about tension. Okay, so pretend there's a bit of steel and I'm pulling it, right? There's a certain point where it just becomes like a spaghetti or stringy cheese thing, starts yielding, right? That's how the metal material behaves, right? It just starts getting. Okay. So, any questions on how we get that? Okay. They teach you this topic first because it's generally like pretty easy to understand. You know, we're just chucking numbers in and we're just trying to find the maximum tension value we can take. Yep.
Is that AT? Is that gross area? Is it the same as?
Oh yeah. So I've basically just done the shotgun explanation. I'll get into the specifics. Yeah. You're right though. Like there's two failure modes, and we'll expand on the next page. Okay. Any other questions from now? Okay. So next is the capacity of compression members. Okay. So doing the same thing, right? We know that F is equal to this times this, right? And NC. Oh, also by the way, this is 0.9 for compression as well. NC is looks familiar. The yield strength times the area of compression. Okay, this is like don't follow like this and stop listening, okay? Because there's more. Basically, if you stop here, you'll probably get the example wrong. You'll be doing motion. So this is like I'm just giving you like a very basic rundown. There's going to be more to all these things I'm saying. This is essentially the section capacity, and there's also going to be a buckling component, okay? And that's what I'm going to explain next. But do we all get this for now? Okay. Okay. Oh, Let's take a break. Sorry, I know this is like we're just getting into it, but okay, we'll take a break and I'll explain the rest. I love you on cliffhanger.
Edged us.
Yeah, dude.
So. I want to go.
Are you doing this course as well, Leo? Yeah. Been playing Minecraft or listening?
I was also supposed to be in the last course as well. So
Yeah.
I think I've done all you need to know.
Multitask.
Yeah, I'm listening right now. You said something about like not looking at half of you just like.
Just follow the idea we can get done.
Yeah.
Did John get the same
You choose it. So mine is
Did John take the same
6 to 8.
No, you didn't take it. I just took it.
You guys might have it.
Why? They didn't hang out.
Super signing on.
Didn't go. You do you? So right. Oh no, Steve's not doing one, is he? I guess he's right.
Do beach visit still. I don't know when. Sunny day?
Yes.
I mean hot day.
Do you know Chinese?
Do you know Tracy's doing what?
If you're doing probably not. Oh, actually, I don't know.
After the current timetable again. It's
Yeah, with
What?
I think you knew the answer to that question before you asked it. Tracy's got
Oh, yes.
Yeah, I'm not looking forward to it.
last like you failed for the next activity.
So what? Tracy's timetable. I'll just ask her later. I'll just ask her later.
When later?
Group selection is on Friday.
Yeah, probably figured out.
Why'd you find out so weird?
Why'd you do group trip? You just want to fill it up.
He told me to do it.
Oh!
No, it really helps. I think it's easier.
You can.
No,
In your one lecture a few weeks ago.
no, I did 4 weeks ago.
You did 4 weeks already?
Wait, you've done 4 weeks of steel.
That's crazy.
You fucking nerd.
This Tom's cooked for me.
What are you doing?
Geotech and water.
It's
It's a normal one, but it's cooked in general.
Are you a HD student? Is that right?
No, I'm HD for structural.
Oh, nice. Let's go. I think, do you ever meet Clarissa?
No.
I think she ran the first year camp before you guys. I ran it with her actually. I think we were like, but yeah. The best term she ever had was this term for you, basically. term 1 of 30th, she ducks like 3 songs. She ducks 3 of those multiple songs.
Well, what marks did she get?
Bro, you got labs like 93. So you do the maths like, we got like 96, 97, 98 or something.
Sorry, what was your name? Henry. I can't believe I'm meeting Sigma lecturers himself.
Oh, we've met before.
No, we met, but I didn't know you were Sigma lecturers.
Oh. I mean like videos.
Yeah, I was just watching your videos.
Oh,
I didn't
okay.
recognize the voice, bro. You don't have a face scan for it usually.
I think I do. Oh, it depends which courses you watch there.
Yeah.
Sometimes it bugs out.
Yeah.
Sometimes, actually, wait, you're scaring me.
Either I watch Sigma lectures or I watch the set song.
Oh, yeah. Sometimes the webcam, like,
Is this going on Smoko Sigma lectures?
I think Sigma lectures.
I put it on there.
Oh, you can do this like you can do where you like upload it to both channels, like you know,
Oh,
like Instagram, like Instagram.
Dude, you're right.
Yeah, you can do that now.
Oh, shit.
Yeah.
I'll be down. I'll ask Leo.
I don't know how to do it because I don't do YouTube, but
If you do it,
I do kind of want to continue, but I think we're waiting for.
I think that's everyone. Yeah, two people. I'll just go back to my seat.
Yeah. Okay, guys. Alright, let's lock in. Okay, so basically, I was looking at it, and it's going to be pretty hard to actually go through compression all today, not gonna lie. But I can like kind of run you through the basics, and there'll be video. Let's go through material strength, and then I'll touch on tension. Okay. So steel has like a very unique, I guess, material curve, right? Because of its metal lattice at a material science kind of level. You kind of have a symmetric material curve, right? So let's say you have stress that's in tension, going that way, and you have stress that's going in compression, right? And then this is strain. Have you guys seen the material curve before? I'm not seeing everyone though.
I saw it once in a solids exam.
Okay. So that's good. Good start. Basically, steel roughly looks like this. Okay, it will continue like curve both sides, but it's mirrored, right? So in tension and compression, it has the same yield strength, which we call Fy, right? F just stands for strength, Y stands for yield. Okay, but for tension design, we actually consider a little bit that happens past the yield strength, which is basically strain hardening. If you remember that from material science, you guys have to do that, right? Yeah. Strain hardening. It's where basically you have these like micro fractures or something in the material, and they start to essentially develop like a they develop like this like resistance. So actually, there's like a little bit of extra juice at the end, right? So it gets stronger, right? Just before it's gonna fail in like a brittle fracture. Okay. So that yield strength, we call that ductile failure mode. A ductile failure mode just means something that's not gonna fail immediately. So that cheesing kind of effect that I'm talking about, like say we pull this and it's like made out of metal and it's like starts to become cheese, right? That's yielding. So that's a ductile failure method. But if we keep pulling it, what it might end up doing is it might snap. Okay, so that's a brittle failure mode. Okay. So in material tests, this is represented by like a pretty sharp drop in its graph values, right? And that value there is called FU, pardon my French. And that just basically means its ultimate strength. Okay. So we have to account for both failure mechanisms. We have to account for what happens if it fails brittlely and what happens if it fails in a ductile manner. Okay. So that's what we're going to cover for tension design. Okay. So another question you might have is how do I find Fy or Fu? Fu specifically, Leo. How do we do this? So It depends on how the steel is manufactured, essentially. There's different grades of steel, right? Most common 300 plus or grade 350, right? And these are just different products, I guess, different material products. Hollow sections are cold rolled, and I'll get into that like later in the course. But in the Australian standards, right, the steel standards. Oh, I actually haven't talked about AS 4100. Sorry. So I talked about AS 1170.0. That's your load combinations book, right, your code. AS 4100 is what this whole course is based on, right? So if you don't have a copy of this, there's a video on Sigma Lectures, which is like how to download AS 4100, right? And so you can follow that, and you can go through your USW library and database and whatever, and get a copy of this. Okay. So in table 2.1 of the standards, we basically have different descriptions of yield strength, yield stress, sorry. And you follow the table, and it's basically based on thickness, right? So generally the rule is the thicker a bit of material is, the lower its yield strength is, and the thinner the higher its yield strength is. Does anyone want to have a stab at why that is? Wait, sorry, repeat that. So say you have an I-beam, right?
Yeah.
That. And you have another one that's just chunkier. That. Okay. Do you see how the web is much thinner here than it is here? The thinner one has a higher yield strength than the thicker one. Does anyone want to guess why? Okay, so it comes down to how these things are manufactured. So in a factory, these things are hot rolled, which means there's, imagine like a cookie cutter kind of form around this, and then molten metal is like pushed through, right, like into the page or out of the page. It pushes the metal, like the liquid metal through, and it cools down as it's going.
I mean, sorry, you finished then.
Oh yeah. And basically the heat dissipates from the edges of it as it cools down. And essentially what you get is the thin web cools more evenly than the thicker flanges, essentially, right? And so you actually end up getting a higher yield strength because it cools more evenly.
It's more flexible as well, right?
It's more flexible because it's thinner, but that's actually not beneficial.
Oh, okay.
For strength.
So that's not the point.
Yeah. Any other questions? Cool. So anyway, it's the table basically. That's the short answer. I just like to explain where every little bloody minute detail comes from. But if I'm going too slow, just tell me to hurry. Okay. So here's the general rule, right? For tension, we have your factored tension load, and we have the capacity equation, right? Oh, sorry, the whole thing's capacity equation. We have the right-hand side, which describes its capacity, okay? So, we have to basically account for material yield failure and fast fracture. Fast fracture is just that brittle snapping, right? Which I was describing earlier. And I like to draw it out like this. So, you know, when I was just like talking about cheese and whatever, this is what I was talking about basically, right? So when you're pulling a bit of steel, it has this kind of necking effect, right? Which is what I was describing as cheese, right? Just, I don't know, it's like to visualize it like that. And it yields. That's what yielding is, right? And this is based on the gross cross-sectional area, to answer your question, Andy. So what that means is the overall cross-sectional area, the one that you can see there. So, yeah, I think I've covered everything here. Covered. Okay. Oh, not covered. The area. So how do you get the area of these sections? Okay. So basically, we're going to start seeing terms like UB, which means universal beam. Okay. And we might see something like 310, 32 UV, whatever, right? UV 32. Okay. So essentially, what this means is engineers have determined the most optimal sizes for steel beams in a wide range of applications. So we call these universal beams. And go to the Lego store, right? All the Lego comes in standardized sizes, right? Shapes and sizes, and they just work with each other. Okay, that's basically what they've done with steel as well. All these steel beams that are universal, they cover like 95% of application that you need, right? Very little of the time you need like a bespoke beam arrangement. Okay, so what does this first term mean? Okay, I'm just giving you an example, right? 310. 310 is how deep the beam is, right? So if I draw an I-beam, right? So the universal beam is an I-beam. 310 is referring to its total depth. Okay. Now this varies a little bit. It'll be like 311, sometimes 312. Slightly changes depending on the exact steel section, but it's an indication of its depth, right? 32 is how heavy it is per linear meter. Okay. So what I mean by that. Okay. So what I mean by linear meter is pretend we have a beam, okay? 1 meter. So we have to do the steel product is standardized per meter, right? And it can just keep going and going. And so if it's 32, that means that's 32 kilograms per that 1 meter. And that's 32 kilograms per that 1 meter, based on its cross-section shape, right? Just like that, right? Make sense? And so you can get heavier steel, which is stronger, but it is more expensive, basically. You can it's kind of proportional, like how heavy the steel is proportional to how expensive it ends up being, right? For the members. Any questions? Okay. So why do I bring that up? We have something called OneSteel, right? OneSteel is a catalog that you can Google, and it's like a PDF, and it's going to tell you all these different types of steel products, right? And it's going to tell you everything you need to know about them, right? So it's going to tell you the area, AG. It's going to tell you the moment of inertia, right? So when you get all these like standardized products, the advantage is you don't have to pull out your notes from solid mechanics and calculate the area of inertia and all that stuff, the area of moment of inertia, because it's already pre-calculated for you. They've already determined all these properties based on these sizes. So it actually makes it very quick for structure engineers to just be like, okay, we're going to use a 310 UV32, and these are its properties, and let's just see if it can withstand loads. That's the way it works, yeah. Okay. That's how you get gross cross-sectional area. Okay. So next, fast fracture. So sorry, I did a huge like ADHD like tangent, but back to fast fracture. It's where you essentially are pulling on it, and it fails brutally. Okay. But the question is, because we know that Fu there, is higher than Fy, right? So when would it ever fail in fast fracture? Because it will always fail in yielding before the first fast fracture. Alright. Perfect, yeah, because you did maths, right? That's right. So you might remember fast fracture is propagated from cracks, right, in that course. So cracking can lead to this kind of brittle failure mechanism and tension. So what happens is when you have bolt holes, which is very common because to connect two bits of steel together, you can either bolt it or you can weld it, right? So bolt holes are like very common because they're much, they're about equally as common, but like, yeah, bolt holes are very common basically. It's basically going to reduce the cross-sections area, okay, these bolt holes, because it's going to, if you imagine this shape, right, the red one, it's not the entire I-beam anymore because the holes have basically eaten away at two bits in the middle of it. Does that make sense? Oh, does that make sense? Okay. And so, yeah, we have to account for that. The other thing is that you might have different fracture patterns, right? So we can have something called unevenly staggered holes. Sorry, staggered holes. So a non-staggered hole just means these holes are like, you know, like in the same plane as the cross section. But staggered holes is when you have, you know, a hole that's off to the side of the other hole. It's a bad description. But you know what I'm saying? It looks like this. Right? But the thing is, which one has more, let's call it net section, okay? AN is A net. So instead of A gross, right? Because A gross is the whole thing, right? We remove the material based on the bulk holes, and we get A net, right? So which one, based on what you can see, has a higher A net?
Second.
So the first one has 2 holes, right? So you know, it should have 2 bits of materials removing. The second one has 3, right? I'm not saying you're wrong, but do you get what I'm saying? There's 3 holes instead of 2. So what's causing the third one, the second one, from potentially having more cross-section area?
Wait, zoom out. I'm really lost. What are we talking about?
Okay, so we're talking about basically this beam over in 3D. We're talking about it coming apart, right?
Okay.
From the other side. Okay. So that's being pulled that way, and then the equivalent shape being pulled that way, right? So, which between the red and the orange one, which one has more cross-sectional area, net cross-sectional area? This is based on the pattern. Okay, I'm just fucking with you guys, to be honest. Like, it depends, basically, is what I'm saying. So, the idea is that if you go diagonally, right, if this fracture pattern goes diagonally, like you see there, it actually adds area. Do you know what I'm saying?
Oh yeah.
It's got 3 fracture holes, but you're basically drawing more of the area off to the side.
Yeah.
And it's basically increasing the amount of area that it can take. Right, which sounds really complicated, but actually there's a very easy formula to determine this. So that's failure mode 1.
When you say area, you mean area is track?
No, area, cross-section area.
Ah.
Do you see the bit that I've shaded red there?
So the holes is not part of the cross section.
Yep, it's a void. The holes are a void, right? Yep. So in red is the net area. So it's the gross area minus the whole area. Okay? So that's the first failure mode. The second failure mode looks like this. Okay? Do you get what I'm saying? So the diagonals add area, but the holes subtract area. So there's formulas for this, okay? We're taking off the diameter of the hole multiplied by the thickness of that. Okay? That's what we're subtracting. Subtract. Make sense? That's what that formula is describing. And also the hole diameter has to basically, let's not worry about base plates for now. You have to add like a little bit of extra around the bolt diameter. So the bolt fits in like that, right? But because of the threads of the bolt, which look like, you know, that like spirally bit in a bolt, the threads of the bolt will also remove a bit of area, right? So that's why we actually have to add on 2 mil, because it's 1 mil around the edge of that bolt. Does that make sense?
Okay, so the hole is just a bolt that's been removed.
Sorry?
The hole is just like where the bolt was put in.
Yeah. I mean, like, so what is a bolt, right? A bolt is a way to tie like 2 bits of steel together.
Yeah.
Right? And you need a hole to put the bolt into, right? So the hole is the void that removes our cross-section area, right? Okay. Makes sense. You know how I said each zigzag, right? So those diagonals is going to add a bit of extra area. That's how you calculate it. So we have something called pitch distance and gauge distance. It doesn't really matter. I always forget which one's which, to be honest. SP and SG. Okay. So pitch is in the direction of the force, right? The tension force, and gauge is perpendicular to that. right? And we just plug and play. They did some shit with Pythagoras. And yeah, they figured out that this is the formula. That's how you do it. Make sense? Yeah, cool. So that's tension, right? So we figure out which bolt arrangement is going to give us the worst area, and then we compare it with sorry. So that gives an AN, right? And then we use FU. Okay. And then we also multiply the whole thing by 85%. The reason we multiply by 85% is because this is like an additional capacity reduction factor. Do you remember how we have 0.9 over here? So you do 0.9, you also multiply it by 0.85. This is because when you have something failing brutally, right, in tension, it's less reliable, so it's more prone to failing at like a unpredictable strength. Right. Okay, so what's KT? So correction factor. So this one's kind of the hardest part to understand, to be honest, in tension, but it's not that much harder than the rest of the stuff that we've kind of got. So these are all different cross sections of bits of steel welded or bolted together, right? And KT is equal to 1 when you have symmetry, right? That's the basic rule of it. Like, there's all these different cases. You might not know what a PFC or anything is yet. You might not know what all these terms are, but that's the rule for now. You know, when you get into the nitty-gritty and you're doing workshop questions, you will find out when they use the case that they're using, right? There's like all these kind of rules with equal angles and whatever. It doesn't matter. The idea is when you have symmetry, your correction factor is just 1. And when you have asymmetry, like for example, this equal angle welded or whatever to something else, you have a reduction factor. It's less than 1. Correction factor is what they call it. Make sense? If you're interested in why, Google shear lag. It's due to shear lag. Okay. Yeah. There's also initial sizing. I'll get into that. Initial sizing is basically like you're working as a structural engineer, and your boss is like, "Yo, we're going to experience this many loads on our bridge. Can you figure out what's the best section to choose, basically, right? What's the best? When I say section, you go to OneSteel catalog. You know, I was talking about like the 310 UV, 32, and whatever. What's the best section to choose to maximize our value, right? Which means like we don't have to pay a crazy amount of money, right? Does that make sense? So like you have your 310 UV, 32, and you have like all these other ones, right? And then it's like this one's smaller than this one. Let's just say, right? So 2 is smaller than 1, 3 is smaller than 2. It's like, what's the most cost efficient number that we can get away with, right? That's what this is. Except usually there's like factors of safety involved. It's like, okay, let's just say like number 2 is the most cost efficient one we can get away with, but it might cause us problems down the line when we're designing something because the architects might move all this shit around, right? And so we might be screwed if we say that. So we're going to go with one that's bigger, because if it's bigger, there's more room for error. Do you get what I'm saying? If loads increase, we're not screwed. Do you know what I'm saying? So that's kind of like what initial sizing is. Initial sizing is like, there's like a, it's a bit of an art, I guess, like choosing how much extra meat you want to pack on, that sounds weird, to your steel structure in order to deal with like uncertainties, basically, right? I think a general good rule of thumb is you go 5 to 20% over capacity, like more than you need to. You know what I'm saying? So that's what this is. So if it's too low, it's unsafe. If it's too high, you waste materials, you waste money, etc. Okay. So this is where like the art of design comes in. Because it's not just about numbers anymore. It's about using your like judgment, about using engineering. There is an example, but I won't go through it. It is included, so if you ever want to look at it, this is how you do it. Initial sizing, whatever, capacity loads, all that. It's a bunch of examples actually. Okay, so because I know this is very late, I'll be covering buckling mostly like online next week or whatever. But I'll introduce you to the general concept, right? Because your week 3 quiz will definitely have tension and it'll definitely have compression. So the idea of compression is unlike tension. So tension, I'm pulling this rod or whatever. I'm pulling this rod, and it's just like it gets more straight if I pull it. But if I push on it, it starts to do this. It starts to buckle. So why does it do this? Basically, buckling is the idea of an elastic failure. Right, so it's an elastic thing that happens. So if I press down on it and then let go, it's going to return to its original state. That means it's elastic, right? So it's not permanent, okay? But buckling can cause problems, right? Because if you imagine, I have a really, really slender, so that's the word for it, a really skinny and long. If I have a really slender column and it's experiencing a high amount of load, you can imagine if I keep pressing down, it's going to fucking snap, right? So it can lead to a premature failure, right? If this was my water bottle, for example, if this was a much more, what's the other word? Stubby. If it's a much more stubby shape, right? So it's much thicker based on this length, and I'm pushing down on it, right? It's going to fail in a normal squash loading. There's not going to be any buckling, right? So this is based on the shape of objects, right? They're going to experience buckling in a different way. Does that make sense? Compression buckling. Okay. So the big part of this course, and like probably the hardest concept to grasp, is compression buckling, which is in the compression portion of the course, and flexural buckling, which is even harder to grasp, and it's in the flexion part of this course. And you did concrete, right? Concrete, we don't really consider we don't consider buckling in that course, basically.
Yeah.
And we don't consider buckling in the flexion part of that course either.
Yeah.
It's a pretty unique feature of steel structures that people try to basically get the most bang for their buck, I guess, in terms of choosing the most slender member possible to achieve some result. And it's because steel is very expensive, right? For concrete, you can just cast a larger block of concrete. It's not going to buckle if it's larger, right? More akin to this shape, right? But for steel, a big part of the design of steel is managing the slenderness of it and managing essentially buckling. That's what I kind of want to leave you guys on in terms of what to kind of look out for in this course. That's like definitely the hardest concept to grasp in terms of the numbers and in terms of all the theory. But if you understand it, you should accept it. Okay, so that's all from me. I'll shut up now, and yeah, thank you. Oh, sorry, questions. Any questions?
Can you go through that material graph and explain to us what's happening with steel at each point?
Yeah.
Yeah, the FYFU graph.
What'd you say?
FU, Leo.
Okay, so yeah, no, that's right. So basically, okay, I'm just gonna talk like in caveman terms, basically, right? So think of stress, instead of stress, think of it like force, okay? And then instead of strain, think of it like delta L. So how much something's gonna elongate in tension, or how much it's gonna deform and squash in compression, okay? So essentially, as we apply more force to something, it's going to strain more, right? Let's just talk about tension. So as I'm pulling on this rod, it's going to stretch, right? Makes sense. So this is the elastic region. Because if I stretch it a little bit, if I apply a little bit of force and then I let go, it's not going to change shape, right? Yeah. Especially for this particular material. What happens with steel is once you essentially apply a big enough force, right, it's going to stop straining. Oh, sorry. If I... Bad explanation, sorry. So, if I keep straining it, okay, It's actually better to think about this, the other way around, as like a displacement governed system. As we keep stretching it, it's going to plasticize and turn into cheese, right? And it's going to cap off the amount of resistance, which is the force that it's going to give back as a response, right? So we keep stretching it. At a certain point, it plasticizes, and then it's giving this flat line amount of resistance, which is the force, right? So that's that plastic plateau there. We get to a certain point, and then the strain hardening effect kicks in, which is what I was describing with the microstructure, and how it actually has like a little bit of extra juice left in the end. And once we reach that point, it actually starts giving a higher amount of resistance, right? Which is where you approach the FU, right? Okay, and then it snaps. Yeah,
I got it.
makes sense. Okay, any other questions?